Yes, please. It's the one without a name on it. Yeah. Okay, great. Hi, everybody. Welcome to the Strong Lensing Science Collaboration Parallel session. I am Graham Smith from the University of Birmingham, and I co-chair the collaboration together with Timo Anguita, based in Santiago, Chile. And after a few words of overview and introduction by myself and then Aprajita, we have a diverse set of talks here covering a nice representation of the different science interests within the collaboration, and also various preparatory work that different teams are doing. And before getting into it, I'd also like to draw attention to how we work in close collaboration with the DESC Strong Lensing topical team. So there's very significant overlap in the people involved in these two groups. Next slide, please. This doesn't seem to work. The remote seems not to work. Okay, so quickly to give an overview of the science interests within the strong lensing community within Rubin LSST. They really cover every aspect of strong gravitational lensing, looking at the dark matter halos themselves that are causing the lensing effect, using lensed supernovae, quasars, and maybe in the future gravitational waves to do time delay cosmography. Also interested in microlensing, using them as gravitational telescopes to study the objects in the distant universe, and also to study the sources themselves, in particular, the very exciting, relatively new arena that LSST will open up in terms of distant explosive transients that are being lensed. And many more. I mean, this is just supposed to be a representative sketch of the kind of things that this community is into. Next slide, please. By way of further sort of giving an overview and just pointing to different topics, and also people and Slack channels to enable people to get in touch with us and get involved in different areas of work. This slide highlights selected active projects. We're going to hear from, at the end of this overview, we're going to hear a little bit from Aprajita on the strong lensing pipeline that we're currently developing in collaboration with DESC, and is now the subject of an inter-collaboration agreement. And we're very grateful to the people who led the development of that recently. We'll also hear from Nikki Arendse from Stockholm, who is leading some nice work on how we're going to go about discovering lensed transients, in particular lensed supernovae, and hopefully we'll also be looking at lensed kilonovae as well. We'll be hearing from Dan about his work around building an all-sky watch list of lenses. So this is one of several important contributions to us getting ready to do very prompt discovery of lens transients in terms of, if you will, delivering Rubin's firstborn, as it were, the first lensed transient discovery of any flavor is a key focus for us that is growing in the next 12 months or so. We also have some in-kind contributions from teams in Mexico and Switzerland on helping us to develop methods to create image stacks with optimal image quality, and also the strong lens database contribution coming from Fred Corban and collaborators at EPFL. We will hear from Tom Collett about for SLSC, which is going to be hugely influential in terms of giving us spectroscopic redshifts of lenses. And there's a group of us on the DESC side led by Simon, on the SLSC and UK side led by me, who are going to be contributing to commissioning. So this is not exhaustive. And if I've missed people's favorite topics, I apologize, but this gives at least a quick survey of the kind of active projects, some of the people involved, where you'll hear more today, and how to reach out. Next slide, please. It's always important to underline the requirements on cadence and observing strategy for any science collaboration or interest within it. I think the most important thing to understand is that we're in the business of doing science with rare objects. And so we are very passionate about having survey strategies that maximize survey area such that we can find those rare objects. Some level of rolling cadence seems to be inevitable. And so among the available rolling cadences, we do have a very strong preference for uniform, as you might expect, but mildly rolling will be okay. So that's the sort of, qualitatively at least, that's the region of parameter space that will not destroy our science and hopefully help it in some cases. A lot of focus is put on sensitivity and image quality in red bands. Most of the lensed objects, especially lensed star-forming galaxies, are blue. And so blue image quality, especially in the especially within what's referred to in the next point in terms of an early reference survey, is very valuable to us, such that we do have good quality in a filter that perhaps not might be used for measuring faint galaxy shapes, but the image quality there is essential for us to do very clean selection of lenses through the lens background galaxies, which is coupled really with the next point about a full wide, fast, deep footprint early reference survey will be key for enabling our early science. We can discover an awful lot of lenses and do an awful lot of exciting science with year one data if it's covering the whole of the wide, fast, deep survey. And close to my heart is also that the target of opportunity program should be flexible enough to accommodate deeper than single visit TOOs. And I will talk more about that in my talk later. At the bottom of these slides, you see how to find out more. In particular, the URL there is pointing to a website that has various documents like our cadence note, our commissioning note, and other documents. So, can everybody on Zoom please mute? Thank you. Great, we're on the next slide. So we have a few requirements on a few data requirements. Lenses tend to be quite small on the sky, but not as small as typical as the alert packet size. So this can be phrased in a couple of ways in terms of our data requirements, hopefully being realistic in terms of the data embargo. But we understand that there will be functionality to obtain cutouts, say up to a few arc minutes in size, as fast as the embargo allows. So this is, we understand this requirement is intended to be met. And for a defined, somewhat limited set of targets, helped by lenses being rare, we're keen on having access to some non-standard alert packets, including subthreshold and potentially also 0 sigma, so very subthreshold alert packets. I've already mentioned image quality quite a bit, but this links to the Mexican in-kind contribution that basically having flexibility to make optimal image quality stacks is going to be essential for our science. Next slide, please. Very briefly on commissioning, there's nothing more on commissioning later in the session. So we made various recommendations in our commissioning note last year, and these center really on two things. One is to use multiply imaged quasars, preferably quadruply imaged quasars, as a strong test of active optics, and also we can also use those in science validation as well. But really within science validation, the key point is to please choose both wide field commissioning fields and also individual LSST cam pointings, those commissioning fields in which we and others before us have already searched in precursor data sets for lenses. This will be really helpful because that will at least give us, if not ground truth zero, but at least give us some information as to what lens population has already been found. So that's the gist of our recommendations for commissioning. And you can find out more from our commissioning note, which is via the link at the bottom of the slide. Next slide, please. Lensing can enable a very wide range of science across the science collaborations, which helps to explain close links with DESC that I've already mentioned, but also with other science collaborations. And so here, to help people reach out to us from other science collaborations, we have our liaison points and their email addresses. We, like many other areas of the Rubin community, we're very open, culture very inclusive, so we just love to get in touch with people and collaborate on shared science interests. So please don't feel shy, just reach out to us and we'd love to hear from you. Next slide, please. Of course, the Rubin ecosystem extends wider than just science collaborations. So we also have these contact points with other elements of the ecosystem. So again, this is how we connect with other areas. So please reach out to us if you have an interesting topic that's relevant to strong lensing. Next slide, please. In terms of joining us, we have no sort of minimum requirement for membership. We have a single level of membership, so it's very flat and open and democratic. And we have regular telecons. Aprajita is making first steps around organizing our first face-to-face meeting. In fact, I think we're polling today for suitable dates. So it's a great time to get involved. Especially, I don't know, is it really post-pandemic? Not really, but as the world opens up during the pandemic, it's a great time to be getting involved. And our website is here. And Timo and I are always up for being contacted by new people, established people. Next slide, please. It's now time to hand briefly over to Aprajita, who will say a few words about the strong lensing pipeline development with DESC. Before we move on to our other talks. Thank you. Oh.
Why do you want to have subthreshold and possibly 0 sigma alert packets?
So the list of positions around which we'd like that will be of order 10 to the 4 sky locations.
Looking at Leanne, just to make sure that she had knowledge.
Of order 10 to the 4.
10 to the 4, 2 arc minute sky location.
Well, I think
for sub-threshold alerts.
I think for yes, I mean we discussed this earlier in the year. I think there are various complexities around how to do that because the number of as far as I'm aware, the number of sub-threshold alerts may be less challenging than slightly larger postage stamps.
Actually, maybe a little bit about the number of. Are you talking about the number of postage stamps you want to request through the cutout server that are larger than a standard postage stamp, or are you talking about positions on the sky you want to be alerted that are sub-threshold?
The latter.
So you want 10 to the 4.
Yeah.
Positions on the sky. I think that's fine. I mean, just to say we don't have a number for this yet. We do have a requirement to support alerting on sub-threshold positions, given that they, if they meet other criteria. We're going to do this for quality monitoring purposes in any case, but we will also do this if there are other criteria that warrant this. I don't think 10 to the 4 is going to pose any image. I mean, we're expecting to send out 10,000 alerts per image. So
yeah,
this is and this is per image, not per night, right? So multiply that by about 1,000.
Lenses are rare. So
exactly. So I don't see any issue with 10 to the 4.
Yeah. I think the bigger sort of mutual complication is is that we would like alert packets that have around location of lenses to have larger cutouts.
Yeah.
And I think my understanding is that's more challenging.
Yeah, it's more that it's not that it's more challenging to make a larger cutout, it's that it will expand the size of the alert packet. And then if we have to do that, we want to do something consistent for every alert packet. So if we do that consistently for every alert packet and you're looking at about 10 to the 4 total, then that's really going to blow up our alert packet size. So just making it larger to support one science case is probably not the right way to go about it. I think the right way to go about it is if you can get the information you need out of the standard cutout that's in the alert packet, and you can say, right, this is an alert of interest, I want a bigger cutout, then you go to the cutout server and you request a larger cutout. If that strategy works, I think that would be the best way to go about it.
It's not ideal, but I have ideas how we might be able to make that work.
Okay, and we can talk about this.
Yeah, thanks for the question. Okay, Aprajita.
Hi, everyone. So I'll try and be quick because I realize we're way over time. So I just wanted to go through a couple of slides that just show the schematic for the strong lensing pipeline. So basically, what you see here is kind of a very simplistic view of what we want to cover in the pipeline. That includes obviously discovery. We need to know where they are. We need to know that they're reliable. We want to know their properties. So there's a modeling component. There's obviously the analysis we want to do. And then with Rubin, obviously, we have this new dimension of time resolved information. So the time delays becomes a really important part of our selection and basically affects every point of the pipeline, at least for the variable lenses. And feeding into all of those are simulations, which are critical for all our discovery as well as analysis science. We want to know a lot about the environments. And then at the top in the blue boxes, you'll see everything that is kind of related to follow-up requirements for strong lensing. So these kind of colored themes are what we want to focus on. And we're basically trying to make a list of requirements using basically all of you in the collaboration, both in DESC and in SLSC, to really flesh these out into our requirements for the pipeline, but also with the view of kind of where we get our resources from, what people are doing in the collaboration, as well as the in-kind program, and also looking towards the Link Frameworks program so that we can plug these gaps and make this a reality. So basically, we're going to start up some discussion groups to kind of organically develop these requirements. We have a template, and over the next few months, we'll be having these basically, I hope, on a cadence of weekly. Well, we'll be tackling different projects to get these things down on paper and start making progress. Could I have the next slide, please? So I'm not going to go through this because it's a horrible, scary flowchart diagram, but you're very welcome to peruse it later at your leisure. But basically, this is just a couple of snapshots of some elements of the pipeline. So the discovery one on the left, and then the kind of zoomed in modeling one on the right. And if you go to the next slide, all I wanted to kind of show is that we've got these different elements, building in the time and the static lenses, and they definitely require different strategies in terms of discovery. And we also have this big need for simulation and training sets. Next slide, please. And these kind of shaded rectangles show where we have some effort coming into the pipeline. Some of that is through the in-kind program. Some of it is also through just our general members. And while it looks like everything's covered or a lot of it is covered, that's by no means the case. There's a lot of room for effort, and we really need you and your input to help us kick this off. So we do have regular meetings. We have a Slack channel called SL Pipeline. Nikki, who you're going to hear about from a bit later, she's going to talk about the lens supernovae work, which she and Remy Joseph have been working on. And that basically is a lot of the effort that's been going on. So again, I won't go through this in detail, and actually for anyone in the room, they can't even see the shaded boxes, so that's not really relevant. But for those of you online, essentially, if you're interested in any element that you see here, just get in touch with me and I'll put you in touch with the relevant group. But basically, we want to look at all scales. We want to look at all types of lenses. We want to look at static and variable, and we want to basically maximize what we're going to get out in early science with Rubin. And as I said, this is all being done in collaboration with DESC, but also we want to build, as Graham showed, with our liaisons, connections wider than those two collaborations so that we're not duplicating, and we're also maximizing from common themes between our collaborations. Everyone's welcome and we need your effort. So I will leave it there. Thank you.
Next slide, please. Oh. Well, no, we can just go to the next talk, which is Nikki Arendse. Yeah. So our next talk is from Nikki Arendse, based in Stockholm, who is currently remote.
Hi, can you see my slides?
Oh, that's right. Sorry, yes. To the local organizers, you won't see Nikki's talk on the Dropbox. She's sharing screen. Sorry, my bad. Yes, we can see your slides, Nikki. We're ready for you. Please go ahead.
Okay, perfect. Thank you. So hi, everyone. My name is Nikki Arendse from the Stockholm University and the Oscar Klein Center. And I will talk about lensed supernovae in LSST and some of the efforts that we're doing now to discover them and use them for cosmology. So as a bit of an overview of my talk, firstly, I'll talk about the Hubble tension and how time delay cosmography can help there. And then I'll go over the lensed supernovae that have been discovered so far. And then I'll focus on the Rubin era, where we will also discover lots of lensed supernovae. And for this purpose, we've assembled a team from the strong lensing and dark energy science collaboration to deal with it, which is the lensed supernova pipeline team. So a really big open question nowadays in cosmology is the value of the Hubble constant, or the present day expansion rate of the universe. And there are two different ways how we can measure the Hubble constant. The first one looks at the cosmic microwave background radiation, so the first light we can see, and then infers parameters at recombination and uses a cosmological model to extrapolate those forward in time to get the present day expansion rate. So this is a model-dependent approach. And then secondly, we can look at more nearby local objects and relate their distances and redshifts. And this does not require a cosmological model because the data points already map out the shape of the expansion history. Now, the first CMB method carried out by the Planck team gets a value of 67.4 for the Hubble constant. But local measurements carried out by SHOES, which use type 1a supernovae, and Cepheids get a higher value of 73. And these values are now in 5 sigma tension with each other. And this is referred to as the Hubble tension. And it's a big problem because it also calls into question the standard lambda CDM model that goes into the CMB analysis. So in order to assess the tension better, we need more independent measurements of H0. And this is where time delay cosmography can come in. So how does this work? Well, we have an observer and then a massive lens galaxy or cluster and a distant source behind it. And light from this object can be magnified and bent by the gravitational potential of the lens galaxy, resulting in multiple images of the same object. So here we see 2 images of this quasar. And when the object is in fact a varying source, so a quasar or a supernova, then the light rays will fluctuate over time, and these variations will arrive at different moments at the image positions because they have a gravitational and a geometrical time delay. And with very extensive monitoring campaigns, we can actually measure this difference in arrival time at the images and therefore compute the time delay. And this time delay depends on the gravitational potential of the lens galaxy and also on the ratio of distances between the observer, the lens, and the source, which is called the time delay distance. And because this is a distance, it scales inversely with the Hubble constant, so we can use it to get an independent measurement. And time delay cosmography has already been applied successfully with lensed quasars. So here you see results from the Holy Cow collaboration, where they combined measurements of 6 gravitationally lensed quasar systems into a precise measurement of H0. So quasars have been useful for this purpose, but when this idea was originally proposed by the Norwegian astrophysicist Sjur Refsdal in 1964, he actually envisioned to do it with lensed supernovae. And lensed supernovae can have several advantages over quasars. So when the supernova is a type 1a, then we can also use the standard candle nature to put extra constraints on the magnification, and this can break important degeneracies. And also lens supernovae are good for understanding more about high redshift supernova physics, and it can probe the innermost structure of the lens galaxy. So after this initial idea from Refstal, it would take another 50 years before the first multiply imaged lens supernova was discovered in HST imaging data. So this one was called supernova Refstal, and it was a very special one because it was lensed multiple times. So here in this panel, you see 4 images of the same supernova, but the models predicted that a year later, the supernova would also appear in another image of the host galaxy at 1.2. And exactly as predicted, it also did. So this was a great test of our lens models and also allowed for a 6% estimate of the Hubble constant, just from this system, which is quite remarkable. And recently, there's been a second discovery of a lens supernova lensed by a galaxy cluster, which is supernova Requiem. And this one is predicted to host an extra image, the 4th image, in 15 years. So we have to stay tuned for this. But even though we have these cluster lens supernovae, we actually expect that most of the supernovae will be lensed by normal elliptical galaxies. And especially in LSST, this will be the case. So, and for this, we have one example that's been published, which is 16 GAU, and it was discovered in the IPTF survey because it was extremely bright for its redshift. And because this was sort of a symmetric system and the mass of the lens galaxy was a lot lower than the ones of the clusters, this led to very short time delays of the order of 1 day. So this is not great for inferring the Hubble constant, but still interesting for learning more about supernova physics. And now recently we discovered a second supernova lensed by galaxies, which is supernova Zwicky. So we have 2 of these objects now, but we would have expected to find a bit more of them, like maybe of the order of 10 or 20. So why is it so difficult to find these supernovae that are lensed by galaxies? Well, mostly because in current surveys, the lens supernovae by galaxies will mostly be unresolved. So here you see the original image of 16 GAU taken by IPTF, and it really doesn't stand out. It could be a normal supernova. It was just very bright, so then they took follow-up observations, and then you can really see the structure of the lens supernova. So this makes it very difficult, and we need to rely on very subtle features of the data in combination with photometric redshift estimates. And then if we do this well, then maybe we can hope to find like a handful of lens supernovae per year at the moment. But this is all going to change drastically with the Vera Rubin Observatory. So here you can see estimates for lens supernovae per year that will be discovered with LSST. And this is both using the magnification method, so supernovae that are very bright and magnified, and also looking for multiple images. And these numbers are really an extreme increase of a few orders of magnitudes from compared to what we have now. But of course, these supernovae will not just fall in our lab. It's actually going to be quite challenging still to find them. We have to go through terabytes of data each night. Many of them will not even look like point sources because you have multiple images together. So it could be that our automatic detection algorithms will reject them. And even the ones that will appear on our radar might also be unresolved, so they will look very similar to normal supernovae. And when we do see the multiple images, because lensing is so rare, it's actually more likely that it's just a normal unlensed supernova, that 2 of them happen to go off in the same galaxy. So there are a lot of challenges involved. And this also led us to ask the question, how can we actually find all these large numbers of predicted lens supernovae that should appear in LSST? And in order to tackle this question, we introduced an effort joined by the Strong Lensing and the Dark Energy Science Collaboration, which is the Strong Lensing Pipeline. Now, Aprajita already introduced this. I will just focus a bit on the simulation aspect of this. So our goal here is to create realistic simulations so that people can test their lens finders and inference tools. And we don't want to just pick one lens finder and go with it. We want to use multiple ones because every lens finder will be sensitive to a different part of the lens population. And in order to create these realistic simulations, we will use synthetic source injection. So this effort has been led by Remy Joseph, and here you can see how it works. So you simulate a fake lens source, and then you take a real galaxy, or in this case, it's a simulated galaxy from the DC2 simulation, but it should also work for real LSST images. And then you inject this lensed one into the real image to get this combined image over here. And so Remy has been leading this so far, but sadly he's moving away from academia. So there will be an opening soon to continue this important effort. So if you're interested, then keep your eyes and ears open. And now I'd like to zoom in a little bit on a specific subpart of the strong lensing pipeline, which is the lens supernova pipeline team. So this team consists of Justin Pirel, Suhail Dawan, Brian North, and myself. And our job is to make sure that the lens supernova or transient part of the pipeline works well and that it's integrated with the total pipeline. So similarly to the strong lensing pipeline, we want to make realistic simulations of the lens supernovae, which will then be injected into images, and then we can use it to test our lens finders and Cosmo analysis methods. And the vision that we have for this pipeline is, first of all, that it should be very flexible. So users should be able to input their favorite lens models, cosmology, observing strategy, and also their favorite transient models. So this means that it's not only a lens supernova pipeline, but if you have a model for a kilonova or a quasar, for example, then you can also use it to simulate lensed simulations of those. And then it should be scalable because we also want to use it with machine learning algorithms. So we need to be able to simulate very large training sets. So the code should be fast enough to do this. And of course, realism, it should resemble real lens supernova data. And this, of course, realism, you can push it as far as you want. Some things that we're working on at the moment for realism are, first of all, transient host correlations. So we don't want to just assign the transient to any random host galaxy, but we wanted to match what we see in actual data. And for this, we're working together with Alex Galliano, who's working on the Scotch catalog, which is a catalog for simulated catalog for optical transients and correlated hosts. So in this case, we would then, if we have a transient type, we could sample from a host population with properties like color, morphology parameters, and the offset between the transient and the host to pick a host that is realistic for the type of transient. And of course, if we talk about realism, we cannot leave out microlensing, and especially for lens supernovae, this will be quite important because the images tend to form quite close to the center of the lens galaxy, where there's a lot of stars and substructure. And this can give rise to additional lensing effects on top of the normal macro lensing magnification. So here you see an overview of a lens galaxy with two supernova images that form here. And then each of these stars and substructures gives rise to their own microcaustics, these white things. And when the supernova expands, then it can cross some of these microcaustics, which can have an additional contribution to the light curve. So here you see two light curves of these supernova images, where the dashed one is the light curve without any microlensing, and the solid one is where we added one random microlensing realization. This can either magnify or demagnify the light curve, or in some cases it could even distort it. So to include this in the pipeline, we're working together with Simon Huber and Joseph Bernardos, who have realistic microlensing simulations. And microlensing could be a real bottleneck because the simulations are quite computationally expensive. You need to simulate these microcaustics and then also have an expansion model of the supernova, convolve it with the magnification maps. So in this case, there's really a bit of a trade-off between realism and scalability that we need to keep in mind. So coming to my conclusions, lens supernovae will be a promising new probe to get measurements of the Hubble constant that are independent from the CMB and the distance ladder. But before we can reap the benefits in LSST and solve the Hubble tension, there's still a lot of work to do first. And that's why we created the lens supernova pipeline team with the goal to create realistic, scalable, and flexible lens supernova simulations so everyone can test their lens finders and inference tools. So does it sound exciting to you and do you want to get involved? We would be really happy with any help we can get. So the ways to get in touch with us are through the Slack channels. So there's one for the lens supernova team and one for the more general strong lensing pipeline. And then we also have weekly telecons alternating between the lens supernova team on Monday and the strong lensing pipeline on Tuesdays. So hopefully with these efforts and also with your help, we will be ready for the first lens supernovae with Rubin. Thank you.
Thank you, Nikki, especially for staying brilliantly to time. We have time for a couple of questions.
I'll carry the microphone to anybody that wants to speak, but can I take microphone priorities and just tell you how
course.
amazing your visuals were. My mind is blown. That was
Oh,
transformative.
thank you so much.
Again. So I'll continue holding the microphone then. Oh.
Hi, Nikki, it's Aprajita. What do you think your biggest challenge is at the moment with where you are with the lens supernovae pipeline work?
Oh, so many. I guess at the moment also the storing lensing pipeline is a challenge because that is actually going to do the largest part of the functionality. So we really need to continue working on that as well. I think for supernova models, well, for type 1a supernovae, we have most of our models. It will be the other types 2, that some of the light curves can be a bit uncertain, especially when you want to simulate supernovae at very high redshifts, where maybe we don't have enough templates to create this. And also supernova expansion models for type 2 supernovae, because this is what we need for the microlensing calculations. So yeah, I would say some of the more difficult to parameterize supernova types, that could be a challenge.
There's a question from Slack from Tom Collett. Are you running this on any precursor data sets? And if yes, which?
At the moment, not yet. I think first we're trying to develop the pipeline that you can either inject the sources into the DC2 simulation or to simulate your own sources from scratch. But in principle, then we could also apply it to existing data sets. Yeah.
Okay, great. Thank you everyone for questions. Thank you again to Nikki. Let's give her another round of applause for a great talk. And our next speaker, I'm glad that my memory is holding up, is Stefan. And I'll just hand straight over to Stefan to introduce his talk.
Thanks for giving me the opportunity to talk today. Perfect.
And Stefan, be aware that some of your slides may not work because the format, the original format was, so just be ready.
Okay. I also have more okay. Okay. That's not the PDF. Yes. Okay. Okay. PDF is fine. Okay. So thanks for giving me the opportunity to talk today. Okay. I hope now you can hear me. I'm Stefan Schuldt. I'm just started a new position at the University of Milan, but this work was carried out during my PhD, which I did with Sherry Suyu at the Technical University of Munich and the Max Planck Institute for Astrophysics. And so here just a quick sketch how strong lensing works, especially with then a lensed supernova. But I think we can skip this thanks to Nikki's talk now. Really good animation and drawing. In principle, the different light passes going here along, and given the difference in the path length, the difference in gravitational potential, we have here the time delay, which we can use, as Nikki already mentioned, to constrain or to measure the Hubble constant. And if we have a lensed supernova, then also to use the first appearing image to predict when and where the next image appears, to then observe the supernova at very early time, to learn more then about the supernova properties and supernova progenitor systems. Because, for instance, for the supernova type 1a, it's still unclear which of the different types are at the end. And this is key part of the Holly-Smokes collaboration. And our strategy is to find lensed supernova, in principle, to detect first as many as possible static strong lenses. this now mainly work from collaborators. Raoul Canameres is very strongly working on this. He also gives later a short flash talk on this. So I don't want to mention now too much about this. We are using mainly deep learning classifiers to scan all different data sets from various surveys and found already several thousand new lens candidates. And for LSST, we expect then on the order of 100,000 new lenses. But I'm now talking more about the lens modeling part, because to predict when and where the next image happens, we need to describe the mass distribution of the central object of the lens by a profile. Since we are using ground-based images, we are using a relative simple profile, a so-called singular isothermal ellipsoid profile, which has essentially 5 parameters: the lens center, the ellipticity of the lens, and an Einstein radius, which gives the mass of the lens. Additionally, we include now an external shear component, which describes the small distortions of the arcs given a very massive object outside of the image cutout. And normally, these parameters are optimized with Markov chain Monte Carlo sampling. This includes a light modeling, where we then assume, for instance, a Sersic profile. And this is very time and resource consuming. So we are really spending weeks per lens to obtain the mass model. And that's not feasible for LSST with 100,000 lenses, and especially because we need this in very short time before essentially the next image appears. And our approach is now to use machine learning, because if the network is trained, it predicts you the parameter values within fractions of a second. This is not completely new. We are inspired mainly by work from Yasha Hezawi and colleagues. The main difference is in principle the resolution. They used space-based Hubble-based telescope images, whereas we are using now ground-based images from the Hyperion Supreme cam, which, as we have heard already, is expected to be very similar to LSST data, and therefore this is really a preparation now for LSST. This is now just an overview of our network architecture, which is at the end a residual neural network. So our input are the image stems from our lens galaxy in multiple filters. And at the end, we predict now 14 values. As I said, we have 7 different parameters. So 7 values are interpreted now as the median for the parameter, and 1 set of values as their corresponding 1 sigma uncertainties. And because of a small scaling correction, we can really interpret these values now as 1 sigma uncertainties. These networks need to be trained on simulated data because we don't have enough lenses with known mass distribution, but we aim to be very realistic. So our input for our simulation pipeline are only real observed data. As the lens image, we're using images from galaxies observed by HSC with corresponding redshift and velocity dispersion from SDSS. And as the background source, we're using galaxies from the Hubble Ultra Deep Field. And at the end, we are simulating with this input and our assumption of an SIE plus external shear profile how the background source would look like if it is lensed by this mass distribution. And then we can add the simulated arcs on top of or to the lens galaxy image and obtain really realistic mock images. And we are generating now on the order of 100,000 mocks to train then our network. Here are now the results of our network. On the left side, the performance for the Einstein radius. The red line is the median. And in general, we are predicting quite well the Einstein radius. On the low side, for very low Einstein radii, we are over predicting because there we have difficulties, or the network has difficulties with the blending of the lens. On the other side, for very high image separation systems, we are under predicting because we do not have that many training data here, because we're using the real velocity dispersion measurements, and there are not so many lenses which are massive enough. The performance on the lens center and the ellipticity are relatively good. It's slight scatter which we have because we are not assuming that the light follows perfectly the mass distribution does not follow perfectly the light distribution. Main problem are on the external shear, because here is the resolution simply not good enough that the network really can detect these small effects from the external shear. These results are now, as I mentioned, on mocks. Even if we claim they are realistic mocks, they are still mocks. Therefore, we did now a direct comparison on real lenses. So we modeled at the end 31 confirmed lenses with a traditional procedure for which we developed CliAutoPy, which is mainly on fully automated pipeline, divided now into these 4 different steps. Preparation, of course, you need some inputs. Then we're doing lens light modeling, a very quick source and image position optimization to refine, in principle, our initial starting values for the mass parameter values. And at the end, we are really doing the full arc light modeling and also source surface brightness reconstruction, which means we have a SLSC profile describing the light distribution from the background object and compute how it looks on the image plane, which we observe. Here now on full example. So on the left side column, the observed image, in the middle, the model, and on the right side, you see the normalized residuals, from top to bottom, the different filters. And at the end, we are applying our trained network to all these 31 lenses, which takes then milliseconds, whereas really, even with the automated pipeline, we need days per lens, and compare them. As you can see here on the bottom left, the network performance compared to our traditional procedure for the Einstein radii is relatively good. Also for lens center and ellipticity, as shown already on the mocks, the performance on the external shear is not so far not really good. Now, very quickly, I've mentioned a side project which we had, has nothing to do with strong lensing, but it's also a preparation for LSST. We developed a photometric redshift network, and the main difference, normally you have as the observed images from your galaxy, and from this you extract different characteristics of that object. and feed these characteristics from a catalog at the end to your redshift pipeline. Either it's a machine learning algorithm or the SED template fitting, and you get out the redshift. And our idea was now, can we not directly use a convolutional neural network? We give the network directly the images and get out directly our redshift. And this works quite well, as you can see here. And we're really going also to high redshift, and we really cover the full range. And yeah, that's just a quick mention for the side project now. And that's now my summary. Thanks.
Thanks, Stefan, for a great talk. Yeah, the audio was good on Zoom. Great. So we have time for a couple of questions. Oh, there is a question? Oh, sorry, interpreting your gestures. So this is a question from Nikki Arendse. Do you see a difference between doubles and quads in terms of the accuracy and precision of lens parameter predictions?
We tested this with our previous modeling network. There we distinguished between double and quads, and yes, in principle, it's performed better for quads. There we also trained separate networks just for doubles and separate network trained just for quads, and there we saw a difference. And of course, especially, for instance, now the Einstein radius is better predicted for quads because there the network has more information to get out the Einstein radius. If for a quad, the network cannot detect the second image, as said, the network has really difficulties to predict the Einstein radius.
Okay, we have time for one more quick question. Do we have anything on Slack? No, I have a quick one. I think it's born of my own ignorance. Are you trying to, in the modeling, are you trying to reproduce the sort of full morphology of the arcs, or are you doing a more sort of traditional reproduction of sort of positions of
You mean
images?
now with the modeling network, or
Yeah.
there we are really just predicting the parameter values for the mass model?
But your the constraints are the pixelized light distribution?
Yes.
Yes. Okay.
So it's a convolutional neural network. The input are the image stems in different filters. And from this, the network gets out the mass parameter values.
That's great. Thank you.
Yes.
I understand. Okay. Let's thank Stefan again for a great talk.
Thanks.
And so our next speaker is Tom Collett, who resides today in the Zoomosphere. Here's Tom.
Hey, so should I share my screen here, or do you have a version in Rome somewhere?
We do have a version here in Rome. Thank you. But if you want, if it's easier for you to just share, then please go for it.
Okay,
whatever works for you.
I'll do that then. Okay, so thank you for having me. I'll tell you a little bit today about the foremost strong lens spectroscopic legacy survey. So this is a survey on foremost for following up strong lenses from LSST and from Euclid. Just as a quick primer on foremost, I think there's essentially four things you need to know about foremost. It is a 4-meter telescope with a multi-object spectrograph that has 2,400 fibers across a 4.2 square degree field of view, and the survey starts in 2024, so approximately the same time as LSST. Within that large survey that's going to be going on for 5 years, a small amount, roughly 0.1% of the survey, will be dedicated to strong lensing. So The goals of this of the strong lensing survey is to get 10,000 lens and source redshifts. 5,000 of those lenses should have velocity dispersions. And as I said, that requires about 0.1% of the foremost time over 5 years. So we've seen some cool science from strong lensing already, but just to remind you that what we observe in a strong lens depends on the mass distribution of the lens, how the light is distributed in the background source, and on cosmological distances. To give some sort of science highlights from strong lensing, just randomly plucked out of the air, cosmic telescope. We can use the magnifying effect of strong lensing to take an image like the one on the left here, de-lens it and work out what's going on sub-kiloparsec scales, reproduce these de-lensed sources. We can learn about dark matter and mass in galaxies. So this is a figure looking at the density profile slope of galaxies as a function of redshift. Red is what we can do without strong lensing with just dynamics, and gray are huge loads of strong lenses. And then the dashed lines on here are simulations. So this is a way of learning about galaxy evolution. And there's a whole other bunch of cool science that one can do with strong lenses. And the exciting thing is that both LSST and Euclid are expected to discover about 100,000 strong lenses each. These lenses will be quite complementary. Euclid will find typically lower mass, smaller Einstein radius lenses, and LSST will find more of the high mass systems. But the problem is, for all this exciting science and all these exciting large growth of population size, without redshift, all you can actually measure is angles. So this is the equation for the Einstein radius. It's a function of mass enclosed within the Einstein ring and some angular diameter distances. Without redshifts, you don't know what these distances are. So you can still measure the Einstein radius very easily, but you don't know what it means. Similarly, for those two science cases I showed before, you can still use lensing without a redshift to learn about density profile slopes, but you've got no way of putting your lenses on this plot. And you can still de-lens what a source looks like, but you don't have any physical scale. So you can't work out what the, it's really hard to do any scientific interpretation of lenses without redshifts. And unfortunately, photometric redshifts are just not very good for strong lenses, particularly for the sources, because these are typically highly star-forming, highly irregular, high redshift galaxies that are intrinsically very faint, and therefore just de-lensed, they don't exist, or unlensed, they don't exist in spectroscopic surveys, and lenses are rare. So the photometric redshifts are hard. We have to go out and get spectroscopy. That's a challenge because, if we're talking about 100,000 objects, well, you can't just go one by one with a big telescope. And similarly, even though we're talking about 100,000 objects, they're spread across the sky. So, you can't do a dedicated multi-object spectroscopy survey for strong lenses. This is the union of LSST and Euclid's strong lenses with a source redshift below 1.8. It's about a third of the total sample. And you can see you're getting strong lens densities of a few per square degree. You can kind of see here the two Euclid footprints, and then LSST is more spread out. So what you have to do to get redshifts is you have to be able to essentially piggyback on a bigger survey that's getting loads of redshifts for all sorts of other reasons. And that's what Foremost is doing. It's this shared focal plane where you've got 10, 15 different science cases going on all at once, and fibers pointing at different targets to do those different surveys. So in any given Foremost pointing, we will have order 10 fibers pointing at strong lens candidates. The reason that I talked about objects with sources below redshift 1.8 is because essentially we're going to get all of our redshifts from looking at O2. There'll be a few lens systems where we find other lines, but our key target is the O2 doublet. And that redshifts out of the foremost wavelength range at about redshift 1.5. We're going to try and look at everything that has a photometric redshift up to about 1.8, just because of photometric redshift outliers. So the moral of the story is essentially that we can't observe, or we can't hope to get redshifts for every single LSST and Euclid lens this way, but we can realistically expect to be getting order 10,000 redshifts this way. Just as an indication on here, these lines, these are O2 doublets at different redshifts, fixed star formation rate, and so you can see sort of things do get fainter as you go to higher redshifts, but it's not, it doesn't fall off hugely. It is actually completely plausible with a bit of lensing magnification that you can actually, with a 4-meter class telescope, observing for about 2 hours, expect to get redshifts for galaxies out to as far as redshift 1.5. Foremost does this with fibers. So one of the things that we have to think about is actually the light that we're getting. So this, these are 6 simulated strong lenses at the typical seeing at the foremost observing site, and this circle is the typical foremost beam. So what that, the typical foremost fiber. So what that means is that you slap the fiber down either on the center and you'll get most of the light from both the lens and the source, or sometimes we'll have to put the fiber down specifically on the source and then separately on the lens. What we find is that actually most of the time we can get all of the flux we need just from one pointing of the fiber. That's helpful because it means that we have smaller integration times. It's slightly harder because it means that the spectra that come out will be blends. This is a discovery of a SLAX lens. You see you've got a elliptical galaxy shown in red on the top, and then there's some rogue emission lines that are given by this blue emission line galaxy spectrum. So what we're essentially going to be doing is something very similar to SLAX, but where we have already from LSST identified that these are our strong lens candidates. That will hopefully enable us to get order 10,000 lenses with spectroscopic redshifts. That opens up some cool new science. I'll highlight 2 areas. One is constraining the dark matter profile in the center of galaxies and the IMF, essentially, of the stars. So this is a figure from Alessandro Sonnenfeld looking at sort of what we can do today with 50 lenses and showing that with 5,000 lenses, we can really nail down both the IMF in lens galaxies and learn about dark matter, which in turn tells us a lot about galaxy formation. The other cool science that we can do with this, leveraging the velocity dispersions, is if you imagine lenses as kind of like a standard mass, where the velocity dispersion tells you something about the mass and the Einstein radius tells you something else about the mass, then we can use this to do cosmology, taking the Einstein radius equation and using it to constrain angular diameter distances. And so this is just assuming all lenses are comparable to the SLAX lenses in terms of their variation, how standardizable they are, then we can expect from 5,000 lenses with velocity dispersions to get constraints on the dark energy equation of state that are comparable to what Planck gives with the CMB. So that's just kind of 2 science cases that we can do with this data set. You know, the point of it is for it to be a legacy survey, and that we should be able to do a huge range of science that we haven't explicitly thought of yet. There are, I would say, 3 major challenges to delivering this program, and I would be very welcoming of any help from anyone, all of these. The primary one is actually finding the lenses fast enough. Foremost and LSST start at basically the same time. Foremost only goes on for 5 years. And so if we are slow at discovering lenses in LSST, we'll have missed the chance with Foremost to observe. You know, some patches will be observed early and foremost, and then we'll struggle to get enough integration time. So that's the big challenge. We really need to be on it with identifying strong lenses. The second problem is false positives. So we haven't got a huge amount of spare fiber hours. So we need to be sure that what we're targeting really is lenses. And the final problem is photometric redshifts. So we don't have enough fibers to target every single strong lens candidate from LSST and Euclid. We can only afford to target the ones that are likely to have an emission line in the wavelength range of foremost. That means we need to get good photometric redshifts for these faint blue sources that are good enough to say, is this a source at redshift 1-ish, or is it a source at redshift 2-ish? So that's kind of an open problem that we could definitely benefit from some help on this. So my summary, strong lenses are interesting. Hopefully you all realize that since you're in this session. For SLS, LS is basically the only way we can get lots and lots of redshifts. But there are challenges, and I hope you'll all be able or interested at least in providing some help with some of them. So thank you.
Thank you, Tom, for a really nice overview of this exciting opportunity for us all. We do have time for a couple of questions.
Hi, Tom, it's Leanne here. Thanks for a nice talk. Can you go back one slide? Just,
Sure.
I'm not sure if I understood, maybe this is my lack of understanding. With point 1 there, are you proposing to operate observations with foremost in like a follow-up mode from LSST? If something's discovered in LSST, then you follow up on this through the whole alert network and so forth?
So I don't think that we can discover lenses through the alert network. I think realistically that's these aren't transients in that sense. But we do basically, we need to discover our lenses in LSST and then as quickly as possibly get them into the foremost observing list so that they can be targeted.
So these would be discoveries that come from an analysis of a data release catalog, not from the prompt processing, the nightly data.
Yeah. So,
okay, all right, I understand your concern now. So you're waiting at least a year before you get the first data release to do this analysis.
Absolutely, yeah.
Okay.
So we'll fill.
Well, you've got data preview too, which maybe will be useful.
Yeah, so we'll fill the first year with targets from HSC and DES and things, and hopefully that'll help as precursor data. But the real large numbers come with LSST, and we need that as soon as possible.
Okay. And a second question for point 3, can you use photometric redshifts computed by LSST and that are released in the data release catalogs?
Almost certainly not, because they're so badly blended. So unless someone does a lens model to try and work out I think it has to be bespoke.
Okay.
Okay, let's thank Tom again for a really great overview.
Thank you.
So I'm going to be Graham for a bit while Graham is giving a talk. So our next speaker is Graham, who's going to tell us about lens kilonova, I believe. I don't know, I just made that up, Graham.
That's okay. I'm going to carry on making
it up. Okay, that's good.
Okay, hi again, everyone. Taking off my co-chair hat here now as a scientist. I'm going to tell you about a project that we've been working on in Birmingham and with colleagues around the world in the last few years, getting excited about the possibility of discovering gravitationally lensed gravitational waves. And increasingly, as our involvement in Rubin and LSST has grown, realized that actually the way to do this science and to unlock this really exciting new field is to go hunting for the lensed kilonova counterparts to the candidate lensed binary neutron star mergers that will be in the LIGO alert stream or LIGO Virgo Cagra alert stream in the mid 2020s. So I'm going to try to give you a brief overview of how we intend to do this and why this is really important and influential in this growing field. You're going to hear from, draw attention to collaborators, in particular Dan, who's in the room, who's going to give the next talk, and also Matteo, who's been very active in this together with us in Birmingham in the last few years as well. Next slide, please. Oh, it should work. Oh, it does. Okay. So the basic idea is that the kind of lensed galaxies that we know and love, whether they're lensed by huge clusters, such as this example, or the kind of galaxy scale lenses that we've seen in the previous two talks, these galaxies are plausible hosts of mergers of binary compact objects, be they binary neutron stars, binary black holes. And that's just like a distant supernova in a lensed galaxy. These can also, these binary compact object mergers can also be gravitationally lensed, and therefore also their electromagnetic emission. So that's the key idea. This will unlock a huge, when we succeed with this, it will unlock a huge amount of science. We're familiar, certainly in this room, with the basic lensing phenomena. So lens magnification will enable us to see objects that are further away than we can see without lensing. That's particularly true for the lensed binary neutron star mergers, because without the help from lensing, you can only see them in the relatively local universe. Also, it will give a new tool in time delay cosmography. There'll be lots of challenges to deal with, but the uncertainty and the arrival time difference will essentially be eliminated as a source of uncertainty in these experiments because of the timing accuracy of the grav wave detectors. Also, as I'll show later in my talk, the expected arrival time differences a significant fraction of them will be sub-day arrival time differences. And so this means, if you think back to Raffaele Magutti's talk earlier today, with an arrival time difference of less than 1 day, the second kilonova image will plausibly be arriving as we're looking for the first one. So potentially we have amazing and unprecedented access to the rising portion of the rest frame UV light curve of a distant kilonova counterpart. And the first detection will also be super exciting for people who are much more familiar with testing GR than I am. But the key thing here is that it will be really influential, like a step change in grav wave polarization measurements. So this gives you a flavor of the kind of science that we're talking about in the next 4 to 5 years or so. Next, do my own next slide. Okay. We and others have been looking for lens grav waves already, and nobody has found a convincing candidate yet. One can basically look for things that appear to be brighter and closer than you expect them to be. One can look for multiple grav wave detections that have overlapping posteriors, most easily visualized as overlapping big bananas on the sky. You can also, especially in our earlier work, you can also hope to possibly with small field of view telescopes try to find electromagnetic counterparts to candidate lens grav waves. The really exciting role of Rubin here is to expand our very small field of view studies from 2019 and 2022 to search the entire sky localization region for counterparts, which will be the main focus of the rest of my talk. It's tough though. Why is it tough? Well, the angular scale of strong lensing is of order arc seconds, which is very well matched to the angular resolution of optical data, as we know. We've known that since the 70s and 80s. But the angular resolution, if you will, of grav wave detection is of order 100 square degrees or worse, and is unlikely to change for the bulk of the population in essentially a signal to noise ratio limited sample. Overlapping posteriors, as I said, that can help. But the overlap of two big bananas is still a pretty large banana on the sky. There's still many lenses per overlapping sky localization for the candidates that people have identified, including this example from Mateo's recent preprint from April this year. The solution is that, well, we know how to localize grav waves. It's to concentrate on binary neutron star mergers and find their kilonova counterparts. And we like to call this multi-messenger gravitational lensing. There are numerous challenges. Challenge number 2 is the way the grav wave detectors work. So they're not on, or even during a grav wave run, they're not on all the time. And so the plot on the left shows you that the typical, they call it a coincidence segment length. So the typical period of time over which multiple grav wave detectors are running in parallel, it very, very rarely exceeds 1 day. And yet for lens binary black holes, which are kind of in the regime that we expect lens supernovae to be in with Rubin, in other words, quite low magnification, strong lensing, the bulk of the probability density for the arrival time differences for lens binary black holes exceeds 1 day. Lens binary neutron stars, in contrast, will have will be more highly magnified and will have shorter arrival time differences, and therefore are a better match to the way the grav wave detectors work. So multi-messenger lensing has an important advantage of increasing the probability of actually detecting an image pair with the grav wave detectors. Further challenge is how do you select a candidate? So implicitly, fairly explicitly here, we're talking about triggering Rubin TOOs. So how might you actually pick out a good candidate to follow up? You're all convinced already that lens binary black holes are exciting, but not very amenable to this kind of study. So I won't sort of dwell on that point. But the very efficient and clean way to select candidate lens binary neutron star mergers is to select them from the mass gap. So they're basically magnified. This arrow is essentially showing a lens magnification. It's magnifying binary neutron star mergers at redshifts 1 to 2 into the mass gap. And so these contours show you the predicted distribution in distance mass space of this population. So the grav wave detectors are already detecting candidates in this region, and the Matteo Bianconi's paper that I pointed out a moment ago was our attempt to follow up some of these in the last grav wave run, and hopefully we'll be continuing that next year. So multi-messenger lensing, selecting an object in the mass gap. It then gets a bit more technical in terms of lensing, so I'll try not to draw too long on the next couple of slides, but the problem is that when you're in the mode of trying to make the first discovery, then you really have to design an experiment that is agnostic to the mass scale of the lens, right? So for time delay cosmography with lens supernovae or lens quasars, then selecting a clean sample of objects that have been lensed by a galaxy as opposed to a more complicated cluster can be a very strong advantage. And but to make this first detection, well, maybe it'll be lensed by a galaxy, maybe a group cluster. We need to be flexible enough to secure that first detection quickly without baking in some assumptions into our approach. And to give you a flavor, this is particularly important because the efficiency of lenses to forming multiple images is a strong function of their structure, which is correlated with their mass. So galaxy scale lenses tend to be steeper, somewhat close to isothermal. Cluster scale lenses tend to have flatter density profiles, and they effectively turn on as multiple images at higher magnifications. In the interest of time, I'll skip this slide, except to highlight that the last point, which is the way to do this in an agnostic way, is to base the predictions based on lens magnification and not on solving the lens equation. So that's the key technical aspect of the predictions in our paper from earlier this year. one might say that really the most fundamental challenge is that there just aren't going to be many objects out there to find. But the predicted rate of lens binary neutron star detections in the next few years is going to become large enough to be interesting. So it's large enough to be ready to make this first breakthrough discovery. So in the next grav wave run, starting, as I understand it, in spring next year, the predicted rate, if you follow the upper edge of the blue band, is starting to get towards 0.1 per year. And then in the overlap of the fifth grav wave run with Rubin, you can see that if we're optimistic, we could be hoping to find about 1 per year. So within the 2020s, it's reasonable to expect that we will detect one, and we need to be ready to do that. I will skip this slide and move on to, from a Rubin point of view, the sort of important plot, which are the predicted R-band light curve of lens kilonova counterparts. So the R-band is the most sensitive filter for this experiment, and the plot is quite busy, but our most conservative kilonova model, in other words, thinking back to Rafaela's talk, red kilonovae, our most conservative model at the kind of magnifications we expect in 05 when Rubin is operating is shown by the lower dashed curve. And so we can see that with 1800 seconds per pixel, we can be sensitive to this conservative assumption for 1, maybe 2 days post grav wave detection. Importantly, we only need one filter. So these are very expensive observations. We'll concentrate on well-localized events. We only need one filter because these fade even faster than kilonovae that are not lensed. So it's more than 1 mag per day. So we don't need colors. Basically, we find something new next to a lens that fades faster than anything we've ever seen before. In a nutshell, is the strategy. And so you hopefully have got the idea that this complements the approach taken for unlensed objects from this morning's talk. I know I don't have time to talk about then how this folds back into the kind of science opportunities that this will create. These things will be trivial to detect with JWST. Just as one very brief takeaway point, very happy to discuss some of the details from this slide offline. And I will leave you with my summary. Thank you very much.
Thanks, Graham.
Are there any questions for Graham?
So you want deeper images, but you can do image stacks, right? Which would not strain the data management team because it will be all 30 seconds images that can be processed with the regular pipeline.
Yeah, so yeah, totally. So we're not talking about each exposure being different. We're just talking from regular. We're just talking about do lots in this place in the standard way and effectively go to, I forget the full depth for wide, fast, deep, but go somewhere close to 5, 10 year depth, but do it tonight, please. And then do it again tomorrow. And then, that's okay. And then we're done. Yeah. It's a lot. It's, yeah. But the data would be, I hope, would be then useful for other science.
So are you essentially talking about running this in a deep drilling field mode? Just in a short period of time, observing a small area, 30-second standard exposures, one filter.
Effectively, it's like a R-band only, deep drilling, time critical, deep drilling field. Sort of for a small number of candidates, right?
Okay.
So the more disruptive it is, the more problematic it will be, the more restrictive we will be on selecting like the really golden candidates. Yeah.
Yeah.
But
so
that's the basic.
This would be interrupting the regular wide, fast, deep. It's a bit like a microsurvey, I guess.
Yeah.
Yeah. So this would need to be proposed as a microsurvey perhaps together with the TO, because essentially it is a TO response, but it works differently. And so, and even though you will go to the depth of the wide fast deep, these images would not be suitable to replace the wide fast deep images because they don't have the cadence, right? So we still would need to revisit that field at a regular cadence for all the time dependent science. So this is not integratable really into the wide fast deep. Not all integrate, yeah. So we can reutilize some of those images, but it's not a zero net gain.
Okay.
It's sounding to me like you propose it as a microsurvey, but it's it has the form of a deep drilling field.
Yes, that's
Okay.
right. Is there a way to propose microsurveys already?
We will find out next week at the survey cadence optimization workshop.
Great, I'll be there.
Excellent, thank you, Graham. Let's give Graham another round of applause for his excellent talk. And can I invite Dan Ryczanowski, sorry, I'm going to say it wrong. Dan Ryczanowski, is that right? Close enough, sorry. He's going to tell us about watch lists for strongly lensed clusters.
Yeah, hi everyone, I hope you can all hear me. So yeah, my name's Dan Ryczanowski. I'm a postdoc now at the University of Birmingham, having just finished my PhD very recently. And I'm going to be talking about building all sky watch lists for strongly lensed transient detection. So what exactly does that mean? So a watch list search is essentially a way of searching for lens transients by looking for candidate transient objects that appear near certain objects within essentially a big list of these objects. So in my research, I'm interested in galaxy clusters as lenses. And so my watch list takes the form of a bunch of coordinates of cluster cores, and then we search for candidate transients within wide field surveys, for example, currently using ZTF to search for candidate lens supernovae, which is what you can see in the bottom left, this bottom left figure here, which is showing one of our watch list clusters. And if you can see the blue square, that's highlighting the center of the galaxy cluster, and the red square is highlighting the position of the candidate supernova. Unfortunately, in this case, this was just a glitch in the ZTF system, so this wasn't actually a true detection, but it nicely displays the example of what the kind of thing that we're trying to do. So this would, in this case, this would be a candidate lensed supernova that we detected through these surveys. So this is a general method that can essentially be applied to any transient, because all it requires is you have a big list of these cluster objects that are your potential lenses, and then you just need a nice wide field survey which will be detecting the transients themselves. So we're currently applying this to supernovae, as I said, with ZTF, but you can also apply this to other things. So we're currently looking at GRBs, as well as Graham was talking about before. This is also applicable to searching for lens kilonovae and gravitational waves. And yeah, the end goal is to find multiple image transients. But the other advantage of this is it doesn't actually necessarily require multiple images to be detected. So this allows you to locate transients which have been magnified but are still singly imaged. So what kind of objects do we want to populate the watch list with? So as I've already alluded to, my research focuses on galaxy clusters. And this plot here is essentially the precursor for most of my work. So this plot shows the optical depth of strong lensing as a function of the mass of the lens. So essentially what this means is how many strong lensing lines of sight are produced by objects of a particular mass. So if we look at the area underneath this, the teal and blue curves, then that tells us the essentially the fraction of strong lenses which are, the fraction of strong lensing which is done by objects of a particular mass. So if you look between the regime of cluster masses, which is from 10 to the 13 solar masses and above, that takes up approximately half of the area underneath this curve. So what this is showing us is that clusters are important to include in any searches for lens transients, as well as looking for those that are lensed by isolated galaxies. So this brings up another question is, okay, so if you decided that you want to include galaxy clusters within your watch list, well, how should you select galaxy clusters? Which galaxy clusters should you choose to populate your watch list with? So there are two obvious solutions. The first one is to include only known strong lensing clusters. The advantage of this is that there are definitely strongly lensed galaxies behind these clusters, so that if a transient did go off in one of these lensed galaxies, then that transient would also itself be lensed. The disadvantage of that is we don't necessarily know what population of, or what proportion of this population of clusters is relevant to the lensing of transients themselves. And then the second option is to just choose all clusters and put all of those into a watch list and then look for any transients that go off near any of those. This has the advantage of maximizing the strong lensing optical depth that you're looking over, but it has the disadvantage in that you're going to have a lot of objects within your watch list that are essentially useless because no transients ever go off near them just by statistics. So we wanted to answer this key question that I've put on the top of the slide to essentially determine whether known strong lensing clusters are relevant to the fraction of strong lenses which lens transients. So this is work I did during the start of my PhD, and essentially we modeled the number of observable galaxies that exist behind galaxy clusters. So the word observable is very important here because if the galaxies are behind the cluster but they're not observable, then they're not going to create multiple images or giant arcs, which allows us to label that cluster as a strong lens itself. So by doing this simple modeling, we discovered that approximately only 1% of typical clusters at 10 to the 14 solar masses actually lens observable galaxies at the depth of the Rubin Observatory. This is the co-added depth after 1 year. So on this plot, it's between the green and the red curves. So this result indicated to us that really what we need to do is we need to be including all clusters. Otherwise, we're going to be actually missing most of them that are relevant to the lensing of transients. So when we look at existing cluster catalogs to populate our watch list with, we discover that in reality, they're not really sufficient for our purposes. So this is because cluster catalogs are currently either restricted in their field of view, as in the field that they detect clusters within, or the redshift distribution of the clusters so you have sort of two categories, one which has restricted field of view, but the redshift distribution of these clusters is larger, or you have the other option where you have very wide field cluster catalogs, but then they don't go so deep in redshift. And in reality, we need both of these things because in order to maximize the number of transient detections, we would like the cluster catalog to be all sky, and we also need the population of galaxy clusters to be relatively high redshift, given that efficient lenses need to sit roughly halfway between the source and us, the observers, and the population of lens transients tends to be pretty high redshift. Obviously, that depends on the type of transient itself, but typically it's somewhere between redshifts 1 and 2. But with existing data, we realized that it's actually possible to detect typical cluster galaxies, so a typical L-star cluster galaxy, out to about a redshift of 1 with current all-sky data that exists. So we had J-band data from the VHS survey in the south and the UHS survey in the north, and also WISE W1 band data from WISE can detect L-star galaxies out to redshift approximately 1, which is what is being shown in this this plot here. Sorry. This plot here on the left, which is showing the color and magnitude evolution of a typical L-star galaxy, with the dashed lines there showing the magnitude limits of each of the surveys. So basically, we so we know that it's possible to detect the clusters within this data, or sorry, that the clusters exist within this data, and that they're detectable. But you obviously need to essentially mine those clusters out from the data sets. So we use a cluster finding method, which is based on a method which was pioneered by Gonzalez et al. And the way that this works is essentially you make a raw density map of galaxies. So you just bin galaxies in different pixel bins, and then you smooth it over with a particular smoothing kernel. So in this example, we use the difference of Gaussians kernel. So that's essentially a Gaussian distribution, which has a sort of large but thin positive distribution, and then a short but wide negative distribution. And this smooths the map out on scales of that are typical of a cluster core. So we use interior Gaussian, which has a width of 45 arc seconds, which is typical of galaxy cluster cores. And then this produces the smooth density map, which you can see here on the right-hand side. So this is showing an example of the galaxy, the smooth density map, and within this density map we can pick out galaxy clusters from the map by looking at peaks in the distribution. And the way that we do that is by using a sort of effective signal to noise, which compares the density of galaxies within the map to a random distribution, and we choose peaks that have a effective signal to noise of greater than 3, and choose those as our candidate clusters, which you can see here in this example map, which also shows a known cluster in the center, which are typically very well picked out by the method. So how well does the method work? Well, we tested it on 125 different regions, which contain known groups and clusters, and some of which of those are strong lenses. And the recovery fraction is very good for large Einstein radius clusters. So you can see here from the plot on the left, a lot of them are above our detection threshold, but as you go to lower Einstein radii, the detection becomes a bit more difficult, although the plot on the right is showing that we can still recover quite a significant fraction of them, especially if we lower the signal to noise ratio cut on our data for a detection. However, lowering the signal to noise ratio limit on our detections is going to increase our false positive rate, which is another thing we've tested by looking at regions which we know don't contain, or regions that are not those that are associated with known clusters, from which we've used CFHT lens data to look for photometric redshift peaks. So this allows us to estimate our false positive rate of detections. And so this is something we looked at for different sets of effective signal to noise ratio cuts. And what we found is that we have, for an effective signal to noise ratio of 5 or more, we have about 6% false positives. If we move that down to an effective signal to noise ratio of 3, then we get a large proportion of false positives. But in fact, the number of detections that we make, so we make approximately 4 times more detections for only approximately 3 times more false positives. So the number of detections outweighs the number of false positives. So that is how we chose what the cut should be. So just looking to the future very quickly, this has essentially just been an outline of the method that we're going to use. We still need to execute the method on the whole sky, so it still requires some thought in terms of tiling strategy and streamlining of the working through the data. We can also refine our recovery fraction and our false positive estimates by comparing to other large cluster catalogs. So for example, RedMapper is one of the ones that we intend to use. And obviously we're going to use this watch list to search for lens transients. As I said, we're using ZTF at the moment to look for strongly lensed supernovae, and Rubin is going to be very useful for this in the future as well. And also other data from Rubin and, for example, Foremost, which we've already heard about, will be great for helping us analyze our false positive rates. So I think I'm just about out of time, so I'll just leave my summary slides up, and I'm happy to take any questions.
Thank you very much.
Thank you, Dan. Any questions for Dan?
Hi, Dan. Thank you.
Hi.
Have you looked into implementing a watch list in LASA for this?
Yes, so that's how we use our that's how we do our search for supernova with ZTF is through Laser. Yep.
And that works right.
Yeah, so we haven't found anything yet, but the list hasn't been assembled fully, so we're still using a prototype watch list.
Okay.
And we anticipate that we can increase the number of strong lensing lines of sight by approximately 3 times by the time we've finished with the finished assembling the list. Yeah.
Okay, cool. Thank you.
Any other questions in the room or online? So I have a quick question, Dan. Have you looked at the other cluster lens finders that are being developed in DESC or in galaxies to compare what you're doing with them or work together at all?
Not specifically. I think the main reason for that is we're not necessarily looking for lenses in the aspect of things that lens galaxies, because we're just generally interested in looking for galaxy clusters which could then lens transients. But it's certainly something to look into. Yeah.
Great. Thank you very much. Let's thank Dan again for
Thank you.
excellent talk. So we now have 2 lightning talks. We have Tanja, who's here, and Raoul, who's online. So I'll hand over to Tanja.
Okay. So I have a few slides, but even though it's like 2 minutes. Okay, I'm gonna completely skip this. I don't have to tell you that lens supernovae interesting for several open questions in astrophysics and cosmology. This is some ongoing work that we are doing with Mateusz Bronikowski, me, and Justin Pierrel. I think he was mentioned several times during the session. As Dan Ryczanowski already mentioned, so we only have few supernovae that have been discovered, astronomy lens discovered so far. Well, 2 in or more in clusters. And one of the problems is that we only have a few clusters that have been exploited as gravitational telescopes so far. And so the point of our work is actually we are making a database with all the cluster lenses. But those, I mean, now that I became aware of his work, we are focusing on those that have very well, very nice data and also quite well studied lenses. So we're also focusing on the looking at all the properties of all the multiply image galaxies that are behind the clusters. And so then we're trying to build a tool that would enable us to get the yields for any survey like Rubin or the Roman Space Telescope, which will be especially important given that is able to see supernovae at very high redshifts, what we're expecting. And then also we are trying to figure out how well we can do cosmology with this cluster lens supernovae. And thank you for your time. And if someone is interested to know more about our work, I'm glad to talk about later.
Thank you very much, Tanja. So we have time for one very quick question. If there is one, otherwise, please contact Tanja on Slack. Okay, no questions online. Okay, we'll move to Raoul then. Thank you, Tanja. Oh, we didn't give Tanja a round of applause. So Raoul, please go ahead.
Thanks. Hi, everyone. Can you hear me? Yeah.
Yeah.
So thanks for the slides and for the opportunity. So to be quick, we have already seen all the great science on strong lensing that will be enabled by LSST. One of the key science is cosmography, and it's one of the main focus of the Holy Smokes collaboration, which I'm part of. So next slide, please. Yeah, so as we've seen, especially with Nikki and Stefan and other people, so especially strong lens supernovae are really interesting for cosmography, as we see on this slide, for many reasons, especially the wide separation systems from LSST will be really important for probing the H-node tension. But for all of that, what we need is robust methods for finding the lenses, of course. So next, please. Yeah, so what we need is dedicated CNNs, as we know are really powerful for finding the strong lenses. But what is actually most useful is a method that is able to systematically identify all the lenses on a very large footprint and without any preselection on the catalog level. So these kind of methods have been developed in our team and tested successfully in the Pan-STAR survey on 30,000 square degrees to classify the 3 billion sources in this survey in a fully automated way. Next. And by training on realistic simulations and having a two-step supervised neural network to classify, we could first, with a photometry, so catch the colors and color gradients of lenses. And then that allowed us to minimize the data, the amount of data to be classified at the second stage with a classical CNN. And this gave us a final list of 10,000 candidates, which is a method that is working and scalable to LSST. Next. So the thing is that, as you see on the top left, there are many nice candidates, but also a lot of false positives. And so for LSST, with the many more galaxies that LSST will find and detect, we need to improve this. So how to test and improve? The best is to go for a precursor survey like HSC, which has a similar data quality. And what we see, and what is nice to see on the bottom right panel, is that for a very dedicated training sets, when we improve the quality of the training set, we can move much more top left and get contamination rates of only 0.01% for very good records. Next. And so that's an improvement that we could test and apply on the HSC dataset for a successful search of static lenses. And now currently, so Alexandra Mello, who is online, is developing new networks to be able to classify images with variable resolutions. And what we are doing now is, as Nikki already introduced, develop other methods for finding lens supernovae, especially with spatial temporal classification of image time series. And what we do is to test on fully observed dataset from the HSC Transient survey in Cosmos to make sure that these networks are really able to separate the lenses, the lens supernovae, from all the variety of other transients that you can see in a real dataset. So thanks a lot. And if you have any question, I will be available on Slack the next days. Thanks.
Thank you. Okay, since we're already quite over and I want to let people have at least chance of getting a cup of coffee, we'll defer Raoul's questions to Slack and thank all our speakers again for an excellent and very varied session. And we look forward to working with you in the Strong Lensing collaboration. Thank you.